Swayam Prabha. Digital India. Educated India.
Previous lecture, if you could recall, we started the chromatography section and we were discussing about the basic concepts in chromatography. If you could recall, we have talked about the very general principle of chromatography, where we have discussed about distribution coefficient and effective distribution coefficient. We have also discussed about the various combinations of stationary and mobile phases. And then we have gone to discuss about three modes of chromatography, that is paper, thin layer and column chromatography. We will continue our discussion on the terms and the performance parameters related to chromatography in this lecture. We were talking about the terms like chromatography, chromatograph, chromatogram, stationary phase, mobile phase and analyte. So, let us continue our discussion further. Now, there are certain other parameters which are very important to assess the performance of chromatography, and we are going to discuss them today. One is retention time. Now, retention time is a characteristic time taken for each analyte peak to emerge from the column, and this is, as I says, characteristic time, because under standard condition it will remain the same, that is for same column conditions, temperatures and other factors, the characteristic time for a particular analyte will remain the same. Then as the retention time is there is another term called retention volume or elution volume. Now, the volume of if we have to define this, then retention or elution volume is the volume of mobile phase required to elute the analyte under standard conditions. Now, elution volume and retention time are related by the flow rate. So, again the retention volume or the elution volume is a characteristic feature under standard conditions, and both retention time and retention volume are related by the flow rate, that is at what flow rate you are moving the mobile phase through the column. So, this flow rate, this relationship is given in here, like it is the volume retention volume equals the retention time multiplied by the flow rate. So, what you have is that if you know how much flow rate is there, you can calculate the retention volume. Now, the flow rate could be influenced by a lot of different factors, that could be physical dimensions of the column, whether column is narrow bore or narrow diameter, or it is a wide bore column, what is the length of the column and all those characteristics. Then it is also influenced by physical characteristics of the particles packed in column, that is what is the size of the particles, shape of the particle, what is the porosity of the particle. For example, if they are packed very well, then certainly flow rate would be small, unless you pump or you make it so happen that you have a higher flow rate through a pumping system. Then viscosity of the mobile phase also will affect the flow rate. So, these are factors which will certainly influence the flow rate, and then therefore, the retention time and the retention volume. So, for a liquid partition chromatographic column, the elution volume is related to volume of stationary phase. Now, it is not only stationary phase, but it is related to stationary phase, distribution coefficient of the analyte between the stationary and mobile phase, and the void volume, that is the dead volume of the mobile phase around and within the stationary phase packed in the column. And this is related by the equation, if you can see on your screen, that is retention volume equals the dead or void volume plus the distribution coefficient and the volume of stationary phase. So, you can calculate again the retention volume if you know these parameters. For adsorption column chromatography, the stationary phase will be replaced by the surface area of the adsorbent in place of simple stationary phase. Here adsorbent surface area will be taken. So, elution volume or what we say retention volume is an important factor to assess that how analyte is being purified. Another very important term and it is a performance parameter in chromatography is the capacity factor or the capacity ratio. Now, the capacity ratio or the partition ratio or we call it capacity factor, this does not have any units and it is the measure of the time spent by the analyte in the stationary phase relative to the time spent in the mobile phase, and it is given by if you in terms of volumes. Here it is given CS Vs upon Cm Vm, where these are the CS is concentrations, CS and Cm are concentrations of the analyte in the stationary and mobile phase. This we have already discussed. Vh is the volume of a stationary phase and Vm is the it is the void volume, and then this is the ratio of which is also called volumetric ratio Vs upon Vm, which is given here. So, capacity ratio is an important factor. Now, like I said, it is the time spent in the two phases. So, it is a measure of the additional time that the analyte takes to elute from the column relative to an unretained or excluded analyte that does not interact with the stationary phase. So, if you have unretained or which does not really partition, will just come out in the void volume and will have a capacity ratio of 0. So, it is a like we can simply say a very simple terms it could be that capacity ratio is a measure of additional time that the analyte spends or takes to elute from the column, and this could be given by this equation where capacity ratio equals Tr minus Tm upon Tm, which is Tr is retention time, Tm is the dead time taken to pass through the column of the void volume, and T prime r is the adjusted retention times, that is Tr minus Tm. So, this you can calculate the capacity ratio on by this equation. Now, in capacity ratio equation, the Tm or transit time of an unretained compound through the column is determined by the length of the column and the linear velocity of the mobile phase through the column, and it is given by this particular equation, that is L upon Tm, where L is the length of the column and Tm is the dead time as we were discussing. So, this way you can determine this particular like through the velocity, linear velocity, you can determine the transit time or the time taken for the void volume to come out. Now, it can be derived from the capacity ratio equation that if an analyte spends an equal time in both phases, that is the stationary phase and the mobile phase, then its Tr equals 2 Tm, that is Tm is the transit time or time taken to come out by unretained analyte. So, then the capacity ratio will be 1. If the analyte spends 4 times as long in the stationary phase as compared to the mobile phase, then the retention time for the analyte will be equal to 5 times that of the transit time or time spent by unretained analyte, and hence the capacity ratio will be equaling 4. So, that means there will be 4 times the amount of analyte in stationary phase than in the mobile phase at any point in the column at any time, if the capacity ratio is 4. So, therefore, capacity ratio is related to distribution coefficient. Since amount and concentrations are related by volume, therefore, the capacity factor for an analyte will increase with both distribution coefficient and volume of stationary phase. Now, capacity ratio values may normally range from 1 to 10. So, this is just to understand in terms of that how much time an analyte spends. More time it spends, more will be the capacity ratio of the column. Less time it spends, less will be the capacity ratio of the column. Another important factor is the separation factor or selectivity factor alpha. Now, it is a relative retention, or you can say separation factor or selectivity factor, and this is the measure of inherent ability of a system to discriminate between two analytes. That is, capacity ratios are reflection of the selectivity of the system. Say if it has more capacity ratio, it will be having higher selectivity, and this is expressed by the selectivity factor, which is given in here. That is, it is a relative retention ratio for two analytes. If you see, it is like it is relative retention ratio for analyte 2 in comparison to analyte 1. So, the selectivity factor is also important in assessing the functioning or performance of a particular column type. Now, the selectivity factor is affected by the chemical nature of the two phases. Some systems like affinity chromatography are highly selective. So, separation of two components is only possible if alpha, that is selectivity factor, is greater than 1. So, unless they could be separate out, as we are discussing different performance parameters, these are important to really purify or to separate two analytes. We have discussed about capacity ratio, we have discussed about selectivity factor, and we will also discussed about retention volume and retention time. Now, another important factor in column chromatography or any chromatography is the resolution actually. Now, what is resolution here? Now, resolution in terms of chromatography is the ability of a chromatographic system, a particular chromatographic system, to resolve or to separate one analyte from the mixture of similar compounds, or we can say to separate two analytes or to resolve two analytes from one another. And this is the measure of success of a chromatographic separation. So, unless you can completely separate two analytes in a column, the whole purpose of chromatographic separation is not served. Now, resolution, which is given by RS small s, is defined as the ratio of the difference in the retention time between the two peaks of the mean of their base width. So, let me say it again. So, resolution is defined as the ratio of the difference in the retention time between the two peaks to the mean of their base widths. What does that mean? Let us see this equation here. So, resolution equals this is TR divided by the W, or which is called the base width of the peak. I will just show you. So, if it is two peaks here, this is peak A and peak B, and these are the retention times for the two peaks, then it is the ratio of the difference in the retention time to the mean of their base width, that is the base width of one peak to the width of another peak. So, that is the average we have taken here. Now, here when resolution equals 1, then the separation of two peaks is almost 97.7%, and the overlap is quite low, 2.3%. And when RS is 1.5, separation is 99.7%, almost complete purification, and overlap is very low, that is of 0.2%. Now, let us see this how this whole thing is happening. If you see this figure here, then what you can see here, that we can see certain peaks in here. Now, if you see here, this peak here there are two completely resolved peaks here, and here you have a retention time of peak A, this one here, which is from origin we are taking, and there is another peak with retention time TRB, second peak with increased retention time, that is this peak comes later on. But you can see these two peaks are almost separate, or we can say these are completely resolved. Now base width here, if you can, this is the base width of the two peaks, and at this point there will be you can say half the width of the peak at the inflection point, and this is calculated in terms of sigma. So base width is calculated to be 4 sigma, and then at inflection it is 2 sigma. Now if you see here, these two peaks, like we say resolution of two peaks, or it can separate completely, like if it's a 1.5 resolution, then it is kind of purifying or separating by 99.7%. If you see these two peaks, then these are overlapping. If we draw these lines here, these are overlapping peaks. What does that mean? These two peaks are not completely separated, or they are not completely resolved in chromatography system or particular chromatography system. So we can say that it is incomplete resolution here. So you can, when you are doing a purification, or you are purifying an analyte by a particular chromatographic system, depending on the efficiency of system, you might get these different types of peaks. Like for example, HPLC will give you a very high resolution separation and very good peaks, that is completely separate peaks, as compared to a simple gravity run chromatography system. There could also be other problems, like if you see here, there is a peak trailing actually. So, and there could be fronting also, where peaks are not very sharp and they kind of drag here, and what you get is you do not get a very good purification. So there could be a lot of different conditions, and you can see the resolution in terms of peak shape and peak heights, how they are resolved, are they separate from each other, and all those things could be looked from this figure. All right. So this was like, resolution is very important factor, and it is a main determinant of the success of a chromatography system. There is another term which determines the resolution, which is called theoretical plates. Now the chromatography system columns are considered to consist of a number of adjacent zones, in each of which there is sufficient space for an analyte to completely equilibrate between two faces. Now each zone is called theoretical plate, and plate height is the length of the column for one theoretical plate, and its units will be in length. So there could be n number of plates in a column, depending on what is the height of the plate, theoretical plate. If you have more number of say plates, or you have a smaller plate height of the plate, then you will have more number of plates, that is n will be higher. And if you have less, plate height is higher, then number of theoretical plates will be lower. So this is like here an equation is given, where h is given by sigma square upon x. So h is the plate height, that is the length of column containing one theoretical plate, sigma is the standard deviation of the Gaussian peak, and x is the distance travelled by analyte within the column. So this could give you the plate height. Now for symmetrical Gaussian peak, the base width is equal to 4 sigma, as I told you, and the peak width at the point of inflection is equal to 2 sigma. So hence the value of h can be calculated from the chromatography by measuring the peak width. Now number of theoretical plates in the whole of the column is given by this particular equation, that is L upon h. Now L is the length of the column, h is the height of the plate, as we have discussed earlier. Now if L and x, like if you have a condition like previous equation, if you could remember, it was sigma square upon x, that could be substituted here in place of h, and what you get is L x upon sigma square. Now, this could be converted to if L equals x, that could be L square. Now, if we consider the position for a peak emerging from the column, so that x equals L, and from the knowledge of the fact that the width of the peak at its base obtained from tangents drawn from the two steepest part of the peak is equals 4 sigma. Hence, sigma equals 1/4 of the base width, and so you can convert the previous equation here, which is that number of theoretical plates equals 16 L square upon the base width square. So, both these things could be measured in in units of time also rather than length, like here we were measuring in terms of length, but you can measure then in terms of time. Then the equation will be something like this, where number of theoretical plates equals sigma 16 Tr upon omega square, and can also be measured in terms of peak width at half the height, and this will be represented by this particular equation. So, there could be various methods particularly to measure this number of theoretical plates in a particular column. Now, the value of n represents the efficiency of the column, and can be very high. It could be say 50,000 plates per meter or 100,000 plates per meter could be a possibility for a very efficient columns, and corresponding value of h can be very small in a few micrometers. So, remember, as the height of the plate or the in terms of length reduces, number of theoretical plates increases. So, as we said that theoretical plates, it is the analyte which separates, it is like different zones present. So, more is number of zones, more will be number of theoretical plates. Now, if we consider, like, just to show you how a peak will look like, if we have to say that on the basis of number of theoretical plates. So, let us if I just want to show you or depict something in terms of theoretical plates, and so if on this axis it is a relative distribution on column, and on the y axis it is a relative solute concentration, so what you have is, so what we are trying to show is that how number of theoretical plates will affect the peak shape or type of particular type of peak of a particular analyte. Now, supposing the theoretical plates are very low number, say there are 10 theoretical plates in a column, then peak will be spread out, sort of, in a sense that peak will not be very sharp peak, it will be something sort of spread out peak where you have n equals 10. So, less the number of theoretical plates, the quality of the separation will be also low. Now, supposing let us increase the number of theoretical plates. Now, let us say if we say there are 100 number of theoretical plates, then there will be certain improvement in the peak certainly, and you will see that the peak is better than the previous one where theoretical plates were 10. So, you can see that as number of theoretical plates is increasing, the base width is also decreasing and the peak is become sharper. Now, let us say if there are 1000 theoretical plates, if there are 1000 theoretical plates, the peak, if I say these are 1000 theoretical plates, then peak is become much more sharper, the base width decreases, and you can see that the amount of solute will remain, though peak height goes up, but amount of solute or the area under the peak might remain the same, but certainly it is coming in a very small fraction here. It's like its distribution in the column, or in the column it is distributed in a small area rather than in a bigger area where theoretical plates were less number. So if you have no theoretical, like if the theoretical plate is 1, then the sample just comes out in void volume. But as number of theoretical plates increases, the analyte also distributes itself into the stationary phase and mobile phase in terms of that adjacent zones are very small, and it distributes more or spends more time in there, and therefore you get a peak which is where it is present in a smaller area as compared to where it is present in a larger area. So this was just to show you the importance of the theoretical plate in here. All right. So this is like both theoretical plates. The theoretical plate will determine the resolution as well. Actually, more is the number of theoretical plates, more will be the resolution. But remember, there is a limit to the increasing plate number by increasing the column length. Like say if you increase the column length, supposing in a particular column length there are certain number of plates, and if you increase the column length, certainly number of theoretical plates will also increase. Now, to a certain extent it will help to improve the resolution, but there is a limit to that, and as you increase plate number by increasing the column length, the retention time and peak width will increase proportionally with L, whereas the peak height decreases as the square root of n. So, the quality of the purification will go down if you keep on increasing after a certain limit. Now, the maximum number of peaks which can be separated by a chromatographic system is known as peak capacity, and it is related to the retention volumes of the first and last peaks. So, remember, unless the first and last peaks, how many like in between peaks could be taken, and if the retention volumes are overlapping, then certainly you cannot purify them, but if the retention volumes of the first and last peak has to be taken to ascertain how many number of peaks could be separated, and this is given by this particular equation here, which could be utilized to calculate the peak capacity of a particular column. All right. So, we have gone through lot of different factors, that is performance factors in chromatography. Now, the success of a particular chromatographic system is judged by its ability to achieve good resolution and is determined by the following some like 3 functions are very important in here, and these are selectivity, capacity and efficiency. So, let us discuss them one by one. The first is selectivity. If you could remember, we are talking about selectivity factor also. So, selectivity is a measure of inherent ability of the system to discriminate between structurally related compounds. Now, this is reflected in their distribution coefficient and capacity ratio values, such that the ratio of the partition coefficient for the 2 compounds gives their relative retention ratio or selectivity factor. So, it is influenced by the chemical nature of the mobile and stationary phases. Now, one example of highly selective chromatographic system is affinity chromatography. Affinity chromatography is highly selective, and it can, like I said, it is the inherent ability of the system to discriminate between structurally related compounds, that could be done by say one example is affinity chromatography. So, selectivity is one important parameter to achieve good resolution. Another parameter is efficiency. Now, efficiency is a measure of the diffusion effects that occur in the column to cause peak broadening and overlap. So, it is influenced by physical parameters of the mobile and stationary phase and by the quality of the packing of the column. Remember, we were talking about trailing of the peak or fronting of the peak, that could come as a problem and your efficiency goes down. So, diffusion effects might occur in the column and they might cause peak broadening or trailing and other problems, and therefore, peak overlap, and so what will happen again, resolution is affected. So, this is also the capacity or its ability of a column to avoid these things, and a lot of physical parameters will also be affecting the quality of the packing, quality of the run in these particular columns. Then third factor is capacity for a successful chromatographic separation. Now, capacity is a measure of the amount of material that can be resolved without causing peaks to overlap. Now, this is irrespective of such action as gradient dilution and temperature programming. So, capacity is how much amount of the material which could be purified without causing two peaks. Like if you are loading too much of the sample, then certainly peak will broaden. Now, if you are loading in such a way that the two analytes, though the peaks are broadening, but the two analytes which needs to be resolved do not overlap, the peaks of those two analytes do not overlap. So, there is a limit to a capacity of that column. If you load too much, then certainly if these two peaks could overlap, and then the resolution goes down. One example is ion exchange chromatography, which has high capacity, and there are other columns like chromatofocusing, which also has a high capacity, because they are these are the commonly used techniques to concentrate impure materials. So, the three things which are important, like we said, selectivity, efficiency and capacity are very important, and resolution is related to capacity ratio, relative retention ratio and plate number by this particular equation. This is n half, that is superscript, and this is selectivity factor, and this is the capacity factor taken into account to calculate how the resolution is related to these factors. So, if you could see, we have discussed certain number of parameters here to understand or to assess the performance of chromatographic system, a particular chromatographic system. Now, chromatography could be qualitative chromatography and it could be quantitative chromatography. In qualitative chromatography, you are simply analyzing a particular analyte for a particular application, but in quantitative chromatography, what you are doing is you are also kind of purifying compound for a certain application, or you want to do something else, like say for example, you want to characterize that particular analyte, say you want to characterize protein or other, say you want to use nucleic acid for further applications. Now, when you have a quantitative separation or you want to quantify certain compound in the system, then you can apply or you can utilize, for example, you want to quantify a particular analyte through the chromatogram, then the area under the peak could be calculated for quantification, and there are methods to do that. Like you know the base width, you know the area could be calculated underneath the peak, and you can quantify the substance. There could be internal and external standards could be utilized for this particular purpose. Another important part in column chromatography is that how the kind of chromatographic systems where it could be simple displacement or simple isocratic run also, that we are going to discuss later on. Now, let us see the principle of column chromatography separation in very simple terms here. Now, if I say there is a column and that column, as we were talking about, that column is divided into separate zones actually, all right. So, in terms of how separation of the analyte will take place, let me show you, then we will go through the discussion. All right. So, if you can see on your screen, as we have showed you, there is a simple column, it could be a glass column, which is enclosed by from one side, and you have filled in here uh, a matrix here. There will be a mobile phase which will be entering. Now this could be called sample, or your mixture of analytes which is in a mobile phase. This could be a stationary phase. Now if I could divide this column into different separate zones here, just to depict, like this is just to understand the whole thing. Now say a sample is present in X quantity here, alright, and just for assumption, the distribution coefficient, that is your KD value, is 1, that is it separates equally in mobile and stationary phase. So what will be the consequences as this whole thing enters, like say separate this areas into different zones here. Now what will happen, as X amount of substance in the mobile phase enters this area, it reaches, like we have taken equal amount here, equal area, and as it reaches here, what will happen, the X will be distributed between the two phases equally, that is phase, the area A, and between the mobile phase. So what will happen here, it will be X by 2, that is half the amount will be in the stationary phase and half the amount will be in the mobile phase. Now supposing more, so once this is gone in, then mobile phase will be put in here. Then extra mobile phase, as it goes along, what will happen, it will redistribute the whole analyte or sample mixture. Now in that way, what will happen, that the X half, like more analyte comes in, then X half which is in mobile phase will move on and will interact here. So X by 4 and X by 4 will come out, and then more mobile as you put in, then this will also be distributed, which is present in the stationary phase. So this will then become X by 4 and X by 4 will go to the mobile phase. So there will be a banding pattern will be created here, which will move as a central thick band and adjacent thinner, or if you say less concentration bands. Now let's go back to discussion and understand this whole thing. That is the whole concept of how the separation is being, or how this whole thing is happening in the column chromatography. All right. So what you have is, when you are doing this separation, it could be depicted by considering a column packed with a solid granular stationary phase, as I have shown you, and it has a particular height which could be anything. Now this one is surrounded by the mobile liquid phase. You will apply the mobile liquid phase from the top, and of which there is 1 centimeter cube per centimeter of column, as shown, as will be showing, I have shown you, but I will show you another figure also. Now if 48, supposing like X concentration, what I was telling you, it is 48 microgram of the compound is added to the column to occupy the position A. Then what will happen, as you put 1 centimeter cube of mobile phase, then it will leave, same amount will leave from the base of the column, and if the compound added has an effective distribution coefficient of 1, as we were talking about, or then it will distribute equally itself between the solid and liquid phase. Now remember, here we are keeping the amounts also equal in terms of 1 centimeter cube, but otherwise we are talking about here is distribution coefficient, and effective distribution coefficient is different. Now as you go along, you add more, same amount of mobile phase is introduced onto the column from the top. The mobile phase in the section A will move down to section B. Now it will take, what will happen, the mobile phase and the amount of the material, that is 48 microgram, will be distributed to 24 microgram of the compound, and 24 microgram will be moving down. So at both A and B, a redistribution of the compound will occur. So there is a 12 microgram in the mobile phase and 12 microgram in the solid phase. So remember, again understand this, first time when the substance or the analyte enters, the 48 microgram is distributed to 24, 24. 24 in mobile phase, 24 microgram in stationary phase. As you introduced more mobile phase, then the 24 microgram which was present in the stationary phase in the section A will be again redistributed into 12 and 12, and as you introduce more of the mobile phase, it will keep on distributing. So, 12 becomes 6, 6 will become 3, and likewise. So, addition of further equal amount of mobile phase to the column will displace the mobile phase in sections A, B and so on, and it will move to C, and the distribution will occur as I will show you in a little while. So, as you keep on moving, the band also keeps on moving here, all right. Let us have a little bit try to understand through this figure. You can see this figure, there are a lot of zones here which are A, B, C, D, E, all right, and here you are adding a particular amount of material is being added in here. So, like I do not know whether you can see it here, there is a 48 microgram in here and it distributes into 24, 24, all right. Now, in 24 in terms here 24 is like what I am saying is 24 is in the stationary phase and mobile phase, and 24 with the mobile phase, as you introduce more mobile phase, goes down. Then as you move on, it will be distributed into 12, 24, 12, because as you are introducing more mobile phase, it will also go down, again 50-50 distribution will take place as distribution coefficient is 1. Then again as you introduce more mobile phase, it will be 6, 18, 18, 6, that is how it will work out. And as you move again you will introduce, it will be 3, 12, 18, 12, 3. So, you have a central band which is thicker or more concentrated, and then you have adjacent bands as they go along, they are more less concentrated. So, your analyte moves as a thick or concentrated central band surrounded by less concentrated bands, and this is how the separation takes place, and this we are talking about when distribution coefficient is 1. Now, this could be a different distribution if the distribution distribution coefficient is somewhat different actually. So, what is happening, that it is quite apparent that after a relatively small number of equilibriations, the compound distributes itself symmetrically within a band. Like I said, there is a central band and there are which is more concentrated, and there are other bands adjacent both on top and bottom of the central band which are less concentrated. So, it should be equally like, so what you see is a mixture of two compounds, one having distribution coefficient of 1 and the other distribution coefficient of say 100, will be able when they are added to the column, they will be able to separate rapidly into the distinct bands, because one will be retained more and another will be retained less. So, all these things which we have studied so far in terms of capacity ratios, in terms of retention, in terms of say selectivity, they will define how a particular analyte is retained. So, more is the distribution coefficient or higher distribution coefficient, and then it is retained more, and subsequently depending on different analytes having different distribution coefficient will be separated, will distribute themselves on the column into different bands and they will be separated. Now, if the distribution coefficient is very close, then it will be hard to separate those two analytes, but if the distribution is quite far up, quite apart, then the separation will be a very easy proposition. So, this is how the whole thing will happen. So, hope you have been able to understand how on a column chromatography separation will take place and the distribution of analytes will occur depending on the distribution coefficients. All right. So, in this lecture what we have gone through is we have discussed about different parameters which determine performance of a chromatographic system and which will determine whether two analytes could be resolved or not. Like high efficiency columns will have high resolution and low efficiency columns will have low resolution. Now, when we say resolution is high, also high efficiency columns will have larger number of theoretical plates as compared to their counterparts, that is low efficiency columns. So, if you have a particular number of theoretical plates, then height of the plate will be smaller and number of theoretical plates will be larger. Likewise, capacity ratio or selectivity will determine the efficiency of a particular column. As we have discussed, three main factors which are important, and these are selectivity, efficiency and capacity. Capacity is important because if you can not purify a particular amount of sample, then you have to do it many runs of that, and it is important that maximum amount of sample could be separated. So, but not all columns are highly have high capacity, like I said, like say ion exchanges have higher capacity. Likewise, selectivity is another important term, where unless a column could differentiate between very closely related substances, it will be very hard to purify them. Like affinity chromatography has very high selectivity, and likewise efficiency, where diffusion and other problems might occur and will broaden the peak or may result into overlapping of peaks. Those things has to be taken into account. So, this kind of completes our basics in chromatography. Now, in the next lecture we will start with we will be explaining about low pressure liquid chromatography and high pressure or high performance, I should say, liquid chromatography systems. Also the basic chromatograph, that is the instrument part, we will be discussing what are the equipment constituents of a, what are the main basic constituents of a chromatograph, and we will be comparing low pressure and high pressure or high performance liquid chromatography systems. And then in the subsequent lectures we are going to discuss about particular column chromatographic techniques, and these are affinity chromatography, ion exchange chromatography, exclusion chromatography and gas liquid chromatography systems. Thank you.